Threesome. Ready for a true coding interview classic? Threesome is a Pattern Mastery 100 favorite and a rite of passage for anyone prepping for phone interviews. It's notorious for tripping up even advanced candidates, partly because it demands both brute force insight and smart optimization. If you can solve threesome efficiently, you're mastering a pattern that unlocks dozens of top-tier problems. Let's break it down and see how the pros do it. Let's break down the challenge. Given an array of integers, find all unique triplets, A, B, C, such that A plus B plus C equals 0. The output must not contain duplicate triplets. The order of elements in the triplet doesn't matter, but each triplet must be unique. Now, let's assess our options. A naive approach would check every possible triple, O(n) cubed time. For interviews, that's a no-go. Instead, we'll sort the array and use the two-pointer technique. For each element, treat it as the first of the triplet and look for two others that sum to the opposite. Sorting helps us skip duplicates and efficiently scan for valid pairs, bringing us down to O(n) squared time. Here's the structure. We are given this list of numbers. Our goal is to find all unique triplets that add up to 0. First, we sort the array to make things easier. Now, we loop through the array one number at a time. At each step, we treat the current number as the first number of our triplet. We will look for two more numbers that add up with it to make 0. We place one pointer right after the current number. This is the left pointer. The second pointer goes at the end of the array. This is the right pointer. We add the current number, the left number, and the right number together. If the total is 0, we save the triplet. If the total is less than 0, we move the left pointer to the right. If the total is more than 0, we move the right pointer to the left.
Let's try to implement it using solution 1. Here we're defining a class called solution. It's just the container where our threesome function will live. Think of it like naming the toolbox before putting tools inside. This line defines the method threesome, which takes a list of integers called nums. Our goal is to find all unique groups of 3 numbers that add up to 0. We sort the list in non-decreasing order. This helps a lot, because once the numbers are sorted, we can use the two-pointer technique to move inward and avoid missing combinations. Sorting takes O(n) log n time. We create an empty list called res, where we will store all the triplets that sum to 0. Think of this as our answers basket. We store the length of the list in n, so we can reuse it easily later. This loop picks the first number of the triplet at index I. We only go up to n-2 because we need room for 2 more numbers after I. This outer loop runs O(n) times. This condition checks whether the current number is the same as the previous one. If it is, using it again would create duplicate triplets. So if it's a duplicate, we skip this index and move to the next I, avoiding repeated work and repeated results. Now we set up 2 pointers. L, the left pointer, starts just after I. R, the right pointer, starts at the end of the list. Together with nums at index I, these 2 pointers will help us search for pairs that complete the sum to 0. We use a while loop to move the L and our pointers toward each other as long as L is before R. Inside this loop, we adjust the pointers based on whether the total is too small, too big, or exactly 0. This inner loop can run up to O(n) for each I, giving an overall time complexity of about O(n) squared. We calculate the sum of the 3 chosen numbers, the one at I, the one at L, and the one at R. This total tells us which way to move next. If the sum is exactly 0, we found a valid triplet. We add this triplet to our results list, res. This is one of the answers the problem is asking for. Now we skip over duplicate values on the left side. If the next left value is the same, we don't want to form the same triplet again. So as long as we see the same left value, we move L one step to the right to skip duplicates. We do the same for the right pointer. If the next right value is the same as the current one, we skip it to avoid duplicate triplets. We move the right pointer one step left each time we see a duplicate value on the right. After cleaning up duplicates on both sides, we move L one step to the right to look for new combinations. And we move R one step to the left, shrinking the window after recording that valid triplet. If the total is less than 0, that means the sum is too small. Because the array is sorted, the way to increase the sum is to move the left pointer to the right. So we move L right by 1, hoping to pick a larger number and increase the overall total. This else covers the case where the total is greater than 0. Now the sum is too large, and we need to bring it down. To reduce the sum, we move the right pointer left, choosing a smaller number from the sorted list. After we've tried all valid positions for I, L, and R, we return res, which holds all unique triplets that add up to 0. And that's how this algorithm works. It sorts the array, chooses a clean starting point for each first element, then uses a two-pointer sweep for each index to find all unique triplets that sum to 0 while skipping duplicates. Efficient, simple, and elegant. Check. Let's walk through this three-sum test case and see why the output makes sense. Nums equals -1, 0, 1, 2, -1, -4. Here, nums is an array of integers. The task is simple. Find all unique triplets A, B, C in the array such that a plus B plus C equals 0. The output we got is -1, -1, 2, and -1, 0, 1. Now let's verify each triplet. Triplet, -1, -1, 2. Sum, -1 plus -1 plus 2 equals 0. All these values exist in the input array. This combination appears at indices such as 0, 4, 3, depending on ordering, but the specific indices do not matter, only the values do. Triplet, -1, 0, 1. Sum, -1 plus 0 plus 1 equals 0. Again, all these values are present in the input. Also important that these two triplets are distinct. There are no other unique combinations in the array that sum to 0 once we account for duplicates properly. For example, we do not repeat -1, 0, 1 in another order like 0, -1, 1. So the final set of unique zero-sum triplets is exactly -1, -1, 2, and -1, 0, 1. The output -1, -1, 2 and -1, 0, 1 matches the expected result, confirming that the three-sum implementation is correctly finding all unique triplets that sum to 0 for this input. Now let's try another implement approach using solution 2. Here we define a class called solution. It's just the container where our three-sum method will live, like a toolbox holding our main tool. This line defines the function three-sum, which takes a list of integers called nums. Our goal is to return all unique triplets A, B, C such that a plus B plus C equals 0. We start by sorting the list in non-decreasing order. Sorting helps a lot with both handling duplicates and reasoning about which combinations we've already seen. This step costs O of n log n time. We create an empty list called res that will store all the triplets we find that sum to 0. Think of it as our answers collection. We store the length of the list in n so we can reuse it in loops without recomputing it. This loop picks the first element of the triplet at index I. We only go up to n-2 because we need space for 2 more elements after I. This outer loop runs O of n times. This line checks if the current number is the same as the previous number at position I-1. If it is, using it again would create duplicate triplets starting with the same value. So if it's a duplicate first element, we skip this iteration and move on, helping us avoid repeated results. For each new I, we create an empty set called scene. This set will help us quickly check whether we've already seen the needed complement for the second and third numbers. Lookups and inserts in a set are on average O of 1. We set j as the index for the second element in the triplet, starting just after I. From here, we scan through the rest of the array with j. We start a while loop to move j forward through the array. For each fixed I, this loop can run up to O of n, giving the main logic an overall O of n squared time complexity, which is optimal for three-sum. For the current pair, nums at I and nums at j, we compute the third number we need to reach 0. If nums at I plus nums at j plus complement equals 0, then complement must be negative nums at I minus nums at j. Here we check if that complement is already in the scene set. If it is, that means we've previously encountered a number that can team up with nums at I and nums at j to sum to 0. When we find such a complement, we found a valid triplet. We append the triplet, nums at I, complement, nums at j, to our res list as one of the answers. After adding a triplet, we want to avoid duplicates coming from the j index. This while loop skips over any repeated values for nums at j so we don't generate the same triplet more than once. Inside that duplicate skipping loop, we move j forward while the next value is the same as the current one. Outside the if, we add the current nums at j to the scene set. This means, from now on, if we need this number as a complement for a future nums at j, we know we've seen it already. We then move j forward to continue scanning the rest of the array for more valid pairs with the current nums at I. Once we finish trying all possible I and j combinations, we return res, which holds all unique triplets that sum to 0. And that's how this algorithm works. It first sorts the array and loops over each number as a fixed starting point, then uses a hash set within the inner loop to efficiently find matching pairs that complete the zero-sum triplets while skipping duplicates. Efficient, simple, and elegant. Check. Let's walk through this 3-sum test case and confirm why the result is an empty list. Input. Nums equals 0, 1, 1. The task is to find all unique triplets that sum to 0. Let's analyze the values. The smallest number is 0. The other two numbers are 1 and 1. Try forming the only possible triplet from this array. 0 plus 1 equals 2. That does not equal 0. And because the array contains only 3 numbers, and all are non-negative, there is no way to form a combination that gives a 0 sum. There are no negative numbers to balance the positives, no other combinations available, no duplicates that change the sum outcome. So the correct output is an empty list, written as an empty bracket pair. The output empty list matches the expected empty list, confirming that the algorithm correctly returns an empty list when no zero-sum triplets exist.
Let's have a quick recap. Breakdown recap. This problem asks us to find all unique triplets in an array that sum to 0. It's not just about adding numbers, it's about identifying valid combinations while avoiding duplicates. The challenge is to make it efficient, because the brute force approach blows up in complexity. Assess recap. We started by comparing different approaches. A triple nested loop would be far too slow at O of n cubed. The breakthrough comes from sorting the array and using the two-pointer technique, which lets us efficiently scan for pairs that complement a fixed number. This brings the time down to O of n squared, a huge improvement. Structure recap. Our plan was straightforward but smart. Sort the array, fix one number, and use 2 pointers to find 2 others that complete the zero sum. Each loop narrowed down possible pairs, and skipping duplicates ensured every triplet remained unique. Implement recap. When we ran the logic, we fixed each number one at a time, moved the left and right pointers inward, and collected valid triplets when the sum hit 0. Sorting made it easy to detect duplicates, so our results stayed clean and accurate without needing extra storage. Check recap. Testing the example confirmed everything worked perfectly. The algorithm found the triplets, -1, -1, 2, and -1, 0, 1, all unique and all summing to 0. Each step showed how the pointers adjusted dynamically, validating both the speed and the correctness. The key takeaway is that efficiency comes from structure, not shortcuts. Sorting and pointer logic turn a brute force nightmare into a clean, elegant O of n squared solution. Master this pattern, and you'll unlock a whole class of problems built around controlled iteration and smart boundary movement.